Oh, additionally, on the 5532, I thought I'd run a spectral analysis on it here, the analog discovery, and so with a 50 millivolt input signal, you see our gain of three, it's pretty uniform, across this, but then towards the end you get this peaking hump, and that's pretty much, if you look closely at the op amp data sheets, all op amps basically do this. Sometimes it's not so clear to see, but you'll usually see a set of graphs, you know, that'll take a look at the frequency response of op amps, kind of as part of the power bandwidth thing, but not necessarily. I don't know. You just got to look for them. I don't know that every op amp has it, has that data sheet, that kind of sample. But hold on, let me, because like in the 5532, for example, I don't really see a graph that shows that. But again, this on semiconductor is the only decent data sheet I've found, and that's not really decent. It has just very minimal numbers of graphs. It doesn't show that, but as far as I can tell, all op amps do actually have a hump like that in it. Um, at some frequency, where they're starting to kind of run out of gas or whatever, and here this starts really early, but that's a sign of distortion. Um, Again, I don't remember what the 072 looked like, but I don't think it had as big of a hump on it. But again, it is a prominent feature of a lot of op amps anyway. I don't know for sure that all of them do it, but this one definitely exhibits that behavior, and you can tell you're getting some kind of distortion, around this level. Now, because again, this NE5532, it's 10 megahertz op amp, and it's showing unity gain down to about 6 megahertz here, which we got it set to a gain of 3, so that may not be unreasonable. I'm not sure, because see, we're running out of loop gain basically. Um, totally ran out of loop gain well before this, in fact. So, but it's I don't know. I'd have to configure it as a unity gain to see if this would be any different. Because again, it should be unity gain out to 1 megahertz, and sometimes you can still get that even with gain feedback on your op amp. At least I've noticed it appeared that way on some. That even if you set your gain to like 10, you still might actually have unity gain out to some frequency, but it's special with a non-inverting amplifier because generally you can't set your gain to be less than 2, and that's one of the reasons. I mean, less than 1 anyway. No matter what happens, that's one of the reasons why sometimes they'll try to filter out high frequency noise on an op amp, with a capacitor across its feedback resistor, but um, that won't always work with an non-inverting op amp because of the fact that its gain can't drop below 1, and when you put a capacitor like that, across your feedback resistor to try to filter out high frequency noise, what you actually want that capacitor's reactance to do is drop below the resistance of your feedback resistor, so you in effect give the amplifier below unity gain, right? And so the higher the frequency, the lower the impedance across the capacitor, and that effectively starts cutting your feedback resistor down to zero, towards zero, as your capacitive reactance diminishes with higher frequencies. That's how it works, but again, that generally you may have trouble doing that with a non-inverting op amp versus an inverting op amp. An inverting op amp you can get subunity gains, but with a non-inverting one you just generally can't. But at any rate, that's why it's I wouldn't have been surprised to see the gain actually trail out here to no less than 1 or so until you get to a high enough frequency, and then it'll all crap out. But since this is rated at 10 megahertz, I don't know. Anyway, I'd have to investigate that. But at any rate, this hump thing, yeah, that's rather annoying. So we can see it peaks right around about 1.6 megahertz. So let's have a look at that real quick with a sine wave. run that, run this, and so what did I say? I said it's, yeah, about one, yeah, one. Let's do 1.5 megahertz. Um, Oops, too far. Right around there. Yeah. Okay. Zoom in on it. Okay. So I got a gain of 0.15 because I'm putting too big of a signal into it. Reduce that. Increase this and this. Decrease this some more until we actually do get some kind of gain. Okay, I'm still not seeing the yellow waveform diminish. Fuckers. Okay, there it goes. Okay, now our gain's kicked back in. Alright, let's take a closer look at the fucking waveform. That's annoying, having to adjust that all the fucking time. Half the time you can't grab it. Yeah, it's hard to tell how good of a sine wave this is. I guess it's okay-ish. Upping it, peak to peak output is 680 millivolts. Okay. But like I said, supposedly our gain's higher here, right? What is our gain? Because according to this, it says our gain is actually 3.3 at this point. So, see if I can adjust it to an amplitude that gives us anywhere near that. Now we're diminishing now. 3 point. Oh, there we go. Yeah. Yeah. So for around 90 millivolts, we start to get a gain boost. So basically, if we either increase the frequency, see, back to a gain of 3 about here at about 1.9 megahertz. So we got increased gain, but then we go down to, 600 kilohertz. It's still a gain of 3 point something. Even at 600, it's a little over 3 now. But, yeah, it's about 3.3, right at 1.24 megahertz or so. So, it seemed to confirm that, but I don't really see a lot of evident distortion at this level, although it does look kind of slightly distorted. But anyway, yeah, I just thought I would go into that, to show you what the kind of output profile of this thing is with a gain of 3. You can kind of test this at higher voltages too. I can put like 500 millivolts, but you'll lose your gain typically. But see, the hump is greatly reduced now, at a 500 millivolt signal, but we're still getting a gain of 3 out in general. But the hump is not as prominent anymore, but it's definitely happening at a lower frequency. So, so with that being said, like I said, that's 639 kilohertz, because that's our slew rate limit. I guarantee you things would be pretty distorted at this signal level in all likelihood, at that frequency. But at least it's still not bitching at me for having out of range signals. Let's go to 1 volt and see what that looks like. Okay, now it's bitching at me. We're still getting roughly a gain of 3, but the hump has almost completely disappeared. But you can switch your probes to like 10x, if you're doing higher signals. And let me try to show you what the result of that would be. Because like I said, you can do your power bandwidth tests like I was doing with the oscilloscope and stuff, but that is kind of cumbersome. So trying to see, investigate the possibility of, you know, okay, well, unfortunately, that reduced everything, and I don't know if I can correct that. Um, let's see. Well, hold on, let me mess with it for a second. Okay, I set both the probes to 10x. It wasn't working for some reason when I tried it last time. But yeah, so not getting any range warnings, but you can see, it's still using our blue line as a trace, even though it's a tenth of a level. But we're still getting accurate gain readings because that's all we care about. Is the gain. Um, but if you look at the voltage, um, it's thinking it's 3 volts output, so, peak when it's probably, well, it's probably 3 volts output in actuality, actually. Um, with a 1 volt input, it should be 3 volts, so hard to imagine why it was griping before. Um, let's do 2 volts because that should give 6 volts output. Yep, yep, it's not bitching. So, and but that's actually 6 volts. Because this is just the peak voltage, so this is actually, not 6 volts, it's actually 12 volts. Um, so if we go to 3 volts, that should be about an 18 volt peak to peak. So basically, you're seeing that for 18 volts peak to peak, it's about 140 kilohertz, which is what we saw. But you got to set both your probes to 10x and don't tell it that. I don't. I tried fucking with these settings when I paused the video, but I couldn't figure out how to do it. But yeah, so for a 10 volt signal, which is a 20 volt peak to peak signal, um, because amplitude, it just means amplitude. It means V peak, not V peak to peak. So when I've set it to 3 volts, it's really putting 6 volts peak to peak, and that's being multiplied by 3 times by our 3x amplifier. So, it's giving us approximately 18 volts peak to peak output. So again, that's a good approximation of our power bandwidth. So, um, if you do the mental math, and you could probably set this thing up to where you could actually enter numbers or something and make it do that, but some custom math channel or something, but to see what the actual data is. But let's set it to 2 volts, okay, which is 4 volts times 3, so that's like a 12 volt signal. So let's see for 12 volt peak to peak signal what our power bandwidth is on it. As we see here, you start seeing it diminish, right around here, about 150 kilohertz, 140 kilohertz. So let's run it here at a lower voltage, okay. Now that's getting us out to 216 kilohertz. So, for 12 volts peak to peak, you can get 216. And, if you get out a calculator or whatnot, you can, like set this voltage to whatever, so that's, so if I wanted 10 volts output, um, peak to peak, that's like 5 volts divided by 3. So about 1.66 volts is where you really want to be. So, and that would be for a plus or minus 5 volt output swing, but 6 volts peak to peak. Alright, so that's, god damn it. I hate that. But yeah, it's about, 240, 250 kilohertz or so. So, that it's given us a power bandwidth on. And if I do, take it down to 1 volt, that's like 2 volts peak to peak. So let's see what its power bandwidth is. Okay, so that's about, you know, 390 kilohertz or so generally is where it starts to divert. So its corner frequency would probably be here about 400, but if just visually, what's visually pleasing is this point where it starts to fall off. So, but yeah, I mean, that's a way you can test your power bandwidth, with the analog discovery, as opposed to, just testing it with 1x probes. Because again, this thing is actually not, it's to the best of my knowledge designed to work with 10x probes. In other words, it's designed to work with the wires that come off the analog discovery, not the, not the little probe fixture I'm using. So, so because of that, I don't think this thing's set up for 10x probes. Let me try it again. Because again, I tried adjusting these when I paused the video that time to 10x to see if that helped. Let's see what happens. Okay, it really didn't seem to make any difference that I can discern. Um, but remember, we're on V peak right now. Um, so if you set it on gain, let me set this back to 1x because I don't know what that actually does in this case. 10. Okay. Alright, so we got a gain of 3, again at 1 volt, because this is how I should have done it. I forgot that I was on voltage. But, because it shows we weren't getting too accurate of a reading of voltage, right? But it doesn't really know because the probes are set to something different. Like I said, you got to kind of trick this thing. Because, if I switch, this is, this should have a 3 volt output, right? But, all right, this should have a 6 volt output. Um, and see, like you'd expect, we got a, 200 kilohertz, bandwidth for 2 volts. But if I go switch it to voltage peak, okay, it's still thinking. Um, well, I guess that's working right. So that should be 6 volts. Now let's try a 3 volt, or well, 3 volt. Maybe go through it again because I kind of wasn't paying attention, I guess. Yeah, let's give this 9 volt. So yeah, it was working. I don't know what the fuck I was thinking. So yeah, 130 kilohertz. But like I said, yeah, you can, switching it back to gain, you know, um, it's looking 3x across the board, no matter what voltage we set it at. You're looking for when that gain falls off. We can even try 5 volts, but it's probably gonna fucking not like that. Because it's trying to put out 30 volts peak to peak, and it can't. The op amp can't do that. It's gonna crash. Um, it could probably. I mean, it couldn't even do 4 volts because that'd be, well, it could just barely. Because that'd be like 24 volts peak to peak because I got powered by a 30 volt supply. Stupid piece of crap. Okay. Why is it set to 76 kilohertz? How the fuck did that happen? Okay, but yeah, it's gained to 3 out till about 117 kilohertz at that level. But again, that's going up to like the max. Well, yeah, it's 24 volts peak to peak. So, but at any rate, yeah, it's pretty but that's how to check your power bandwidth basically. So you got to kind of pull the thing, and you know, again, you know, it's a pretty useful tool, but it's better than farting around with a scope and the frequency generator and trying to adjust it until you see the waveform start to decrease. So, like I said, normally I don't use it. I just use it. At low signal levels, because oftentimes you need to have it at low signal levels, otherwise it'll, if you're doing a gain of 10x amplifier, 10x amplifier, I mean, you probably wouldn't want to put any more than a volt across it because that'd be 20 volts peak to peak. So, God, and like I said, if you're doing filters, you're actually doing really low levels like passive filters and stuff. So in fact, you got to actually kind of set it up for decibels and adjust its range so you can actually see the negative scale of when it comes to decibels. So which you can look at here. So and this thing down here, by the way, is a I'm not really sure what it is. I was trying to get imaginary. I was trying to see if I could do what I can do with the nano VNA and have like the actual impedance, read capacitance and inductance off this thing, like you can with the impedance analyzer they have here, but that requires a special fixture and shit. And it's not good for testing like general purpose filters and shit so much. So like LC resonant filters, for example, and I was just wondering if you can get the imaginary components out of it, and see what the inductive element, because this is kind of like a Smith chart, but not really, but it does actually behave like one. That's why I have this set up this way, because I was actually testing some just passive LC filters and shit yesterday. So, but if you're wondering what that is, that's a custom channel, and you can go select its default is real or whatever, but you can select real, imaginary, phase gain, etc. And there are different modes that the thing can be set in. Linear, logarithmic, but you got the units, which can be in decibels, watts, henries, or farads, or ohms, or I guess that's reactance. I guess what's what X means, but I don't know. I haven't been able to correlate that, but it is interesting because you can see this do interesting things, like when you have a notch filter or whatever, you can see clearly where the dip is, where it's not as evident up here sometimes. But at any rate, that's what that was. So anyway, I think that'll pretty much cover that issue. So which I neglected to cover in the last video, but it got long anyway. So cheers.